Hi, we're going to discuss Chapter 9. So there are some huge differences between Chapter 9 and Chapter 8. Chapter 9 is discussing um, uh, confidence intervals in estimating population parameters, um, that being the population proportion and population mean. And then we'll also see that there's an additional section which we will not be covering in this video, but we'll be covering later in a different video on estimating population standard deviation. But for now, we're going to be doing population mean and population proportion, starting with proportion first. And now, the huge difference between Chapter 9 and Chapter 8 is that in Chapter 8, we were given the parameters in in the um, for the for mean or proportion, depending on which parameter we're dealing with. So now we're trying to estimate these parameters, but some similarities between Chapter 8 and Chapter 9 is we're going to be using the same exact equations, just in a slightly different way, but I'll show you how we derive the equations in Chapter 9 from the Chapter 8 equations. So let's go ahead and just think about what's going on with the with using population proportion. So section 9.1 is on estimating population proportion. So yeah, we're going to be estimating the population proportion, which is determined by using confidence interval. So if we're trying to do a for example 95% confidence interval, they mention 1 minus alpha times 100%. This is kind of like a 95% confidence interval, where alpha, for 95%, alpha is equal to 0.05. If you remember, 0.05 or alpha represents the area on the tails. So so I'll just show you kind of a picture using 1 minus alpha times 100%. So the area here and the area here adds up the shaded region. So alpha equals shaded region. So this is alpha over 2, and this is alpha over 2, since we're splitting it up into 2 equal spaces. So that there's the shaded region, and the portion in the middle is equal to 1 minus, because it's the complement, because it's area remaining, 2 times alpha over 2, because there's 2 alpha over 2 areas, which equals 1 minus alpha. As you can see, you can simplify that to alpha. So the area in the middle is 1 minus alpha, and if we think about this, if we're going to convert this into a percentage, that would be multiplied by 100%. So this would be like well, we'll just, for example, 95%. Example, 95%. We have 0.05 as our shaded region. I'll shade it in a second. The shaded region here, where this is 0.025 and this is 0.025. Okay, so this should be familiar. So this is a 95% confidence interval, so the area on the tail is 0.05, and the area in the middle, it shouldn't surprise you, is 0.95, 1 minus these two here. So we would get 95% by multiplying this by 100%, converting it to a percentage form. So yeah, hopefully that makes sense. So so when we're doing confidence intervals, for example, a 95% confidence interval, what we want is the middle 95% of our normal curve. So if we're going to think about what we were dealing with before, well, first off, the only information that we have, we don't have any information on the parameters. We don't know what the original distribution looks like, but we want to figure out what the original distribution is. In this case, with proportion, we want to know, if you think back from chapter 8 when we're dealing with proportions, the original distribution, what we know about the original distribution is P, right? The population proportion. But in this case, we don't know the population proportion. We want to estimate the population proportion. And the only way we can do that is with the statistics gathered from sample data. So what we do is all the information that we have is p hat. So we're going to be gathering data. And find p hat, because that is the best estimate of our population proportion. And as you remember, estimate, since this is the best estimate of our population proportion, we refer this to as the point estimate of our population proportion. So this is point estimate, right? Okay, so they mention that in the book. So and using the equation from chapter 8, we have the z-score equation. Z equals p hat minus p divide p 1 minus p divide n. Okay, so that we're actually going to use this equation from chapter 8 to derive the confidence interval equation. So notice that if we're looking at this right here, notice that the z-score that's associated with this value right here is negative z alpha over 2. And this right here is z alpha over 2. So the subscript represents the area on the tail, and so that would be negative z alpha over 2 and z alpha over 2. Okay, so you'll see where this comes into play. So using the z-score equation from chapter 8, we can derive the confidence interval. But one little thing I'm going to change, and hopefully it doesn't throw you off, is that we're going to change this to a hat and this to a hat. And I'll explain a little bit more in a second where this comes from. Now, we can solve for, our objective is to solve for p, because we're trying to estimate what the population proportion is. That's p. So let's go ahead and try to solve for p here. So what we're going to do is we're going to multiply both sides by what's known as the standard error in this section. They refer to this as the standard error. But we're going to multiply by that, and we'll obtain p hat minus p equals z times the square root of p hat 1 minus p hat over n. And then we will go ahead and we're trying to solve for this, remember, so we're going to subtract by p hat. So that would be, so we'll continue over here. So we'll have negative p hat, or sorry, p, or negative p equals negative p hat, so we're subtracting by p hat, that's what we'll obtain, plus z times the square root of p hat 1 minus p hat divide n. And now the last thing that we need to do to estimate p is we need to multiply both sides by -1. So the last step is p equals p hat minus z. I'll leave a little bit of room right here, and you'll see where, or why in a second. P hat 1 minus p hat divide n. Okay, so as you can see, this looks very similar to the confidence interval equation that we obtained in section 9.1. Some subtle differences, and I'll explain where they come from, is first from here. So remember that I mentioned that these scores for 1 minus alpha times 100% confidence interval represents negative z alpha over 2 and z alpha over 2. So we can solve for the proportion that corresponds to that z-score by substituting the appropriate z-score. So these are just general because we can, like this would be negative 1.96 and 1.96, right? So we're just putting in general values for our general equation. So we would have alpha over 2 for a subscript for our z, and since we have a minus and a plus, we do plus or minus. So that's where our plus or minus z alpha over 2 comes from in the confidence interval. And actually that's the only difference. And that's the only thing I really needed to change. So it's just that plugging in the plus or minus and representing or putting in the subscripts. So as you can see, we are estimating our population proportion with this confidence interval, and we're using the best values we have to do that using the point estimate. That's all we can base it off of, is off of our sample. So we're using our sample to estimate our population proportion, and we're obtaining this confidence interval. And now we have some terminology, and I'll explain that. Actually, I'll get to the terminology after I go over the estimating the population mean. So this is going to be really quick. So we do the same thing for population mean to obtain the equation, and I could lead this up to you, but yeah, actually I'm going to have this be like kind of a little task for you to do on your own. So using the equation from chapter 8 that we obtained, similar to the one we just used for population proportion, we can do the same thing. So, and there will be a slight difference. So as you can see, we have z equals x bar. Actually, it's more appropriate. I'm just going to say this really quick. This is estimating population proportion, but this video we're actually going to do all. Well, we're going to do 9.1 and 9.2. So it's more appropriate to say, well, actually leave that. I'll just say this is our section 9.2 part of the. This should all be reviewed to you because you covered this last class, so I don't feel bad by combining two sections in one video. So anyways, this is section 9.2, and you're going to show this on your own, and it's almost identical to the population proportion. Just solve for mu, because that's what we're trying to estimate, is using this equation right here, and I'll give you a clue, and it will make sense. Now, we're trying to estimate the population parameters, right, in Chapter 9, using confidence intervals. The only thing is that since we're trying to estimate this, we're going to solve for this. I'll just do it. So one big difference is that we don't know sigma. We only have a sample data. So the best thing, the next best thing to the population standard deviation is the sample standard deviation, which we will be able to obtain from a sample because that's all we have. So instead of using sigma, we're going to use S. And as you remember, that when this z-score equation that we have right here does not follow a z-score equation. It follows a t-score equation, which I actually forgot about just a second ago. So it's probably best that I did do this. So so there's a lot of things crossed out here. So I'm going to write down t equals x bar minus mu over s divided by the square root of n. So it's very similar to Chapter 8, but we had to change a few more things. Not only just the parameter that was used, like p to p hats, like in the proportion, but we had to change sigma to s and also z to t, because when we use this extra variable s that changes from one sample to the next, it changes the shape of the distribution to a t distribution. And a t distribution, the only difference between a t and a z distribution, it has wider tails, fatter tails. So z would go down like this. So a t distribution, they have fatter tails. So that is a t distribution. Okay. So and you know how to use a t-score table, a t-table. So we can go ahead and use this same idea, and the same things apply. So if you want a 95% confidence interval, for example, well, you can look at the previous picture; it's almost identical. 1 minus alpha, and just using the general, negative t alpha over 2 and t alpha over 2. Actually, shaded up here. Fatter tails. So anyways, yeah, it's kind of the same picture, but it will make sense. But since they're fatter tails, and we want to obtain, like, for example, 5% for alpha, we would actually have to go wider because they're fatter tails to obtain a smaller proportion, the same proportion. We have to go wider out since the height is yeah. Hopefully that makes sense. So these values are usually bigger than the z's. So we had 1.96 for 95%. We would expect that to be a lot larger because of the fatter tails. So anyways, solving for this, we would obtain multiply by our standard error, s square root n times s over square root n. So we obtain x bar minus mu equals, I'm actually going to move this to the left side, t times s divided square root n. And then we want to solve for mu because that's what we're trying to estimate with the confidence interval. So negative mu equals negative x bar plus t times s over square root n. And now we multiply by -1 and we obtain mu equals x bar minus t times s over square root n. Okay, and similar to before, since we have these two values here and we want to find the t-score that corresponds to obtaining the middle 95% of our t distribution, we want to substitute the subscripts of alpha over 2 and the plus or minus to obtain both t-scores. So that would be plus or minus t alpha over 2 times s square root of n. And that is the confidence interval for mu when all we have given is s and x bar, which we gather from, and n, of course, our sample size. So our sample standard deviation and our sample mean, which we can obtain from our sample, of course. So there we go. Our confidence intervals for population proportion and population mean. Okay, so those are the two equations we deal with, and some terminology. Let's go ahead and talk about some terminology really quickly. Let's go to the next page. So you'll be asked this on the homework for sure, but let's just write down the confidence interval. We already know confidence interval. The confidence interval for I'll just put 4 ... for proportion will is we already mentioned this. It would be p hat plus or minus z alpha over 2 p hat 1 minus p hat divide n. Okay, so we already mentioned that, and then for mean, we have x bar plus or minus t alpha over 2 because it follows the t distribution. Or sorry, multiply. Let's ignore that. That was the bad. Times s square root n. Divide s divided by the square root of n. So there's our confidence interval. And I'll say that this is the confidence interval for 1 minus alpha times 100%. Okay. And then now we have some other terminology, our point estimate. Let's just do that really quick. Point estimate. Our point estimate for proportion, our best thing for estimating p is p hat. That's our point estimate. Similarly, for mean, our best estimate for mu is x bar. Okay. All right. Now we have some other terminology. Our standard error. Our standard error for proportion would be if they ever mention standard error in a problem, what they're referring to is this part right here. Remember, standard error is the standard deviation, is similar to the standard deviation of our sample distribution from chapter 8. So as you can see, that would be for proportion p hat 1 minus p hat. Okay, it's okay. So that was our similar to our standard deviation of our Bernoulli distribution. Okay, except for we have hats. And for mean, that would just be S. Oh, sorry, over N. My bad. So yeah, the standard error is this whole part, not just the numerator. So the standard error is this right here, and that right there. Blah. What's wrong with me? Okay. Yes. So that is the standard error for the proportion and the mean, if they ever ask for that in the problem. And then the margin of error of and margin of error, we use that variable, margin of error. So the margin of error is including the z or t-score, depending on which variable you're estimating. So that would be, for proportion, that would be z alpha over 2, or yeah, z alpha over 2 times the square root of p hat 1 minus p hat, divide n. And then for mean, it would be t alpha over 2 times s over the square root of n. Okay? So those are your margin of errors. Okay? And you, since that's margin of error, you can say E equals. And you'll see where that comes into play in a moment. But just some terminology. We have confidence interval, which is the entire equation. And then we have point estimate, standard error, and then margin of error. And now for margin of error, we have some other ideas that we use. So for proportion, if we wanted to actually, let's go ahead and do proportion second, because that one's actually a little more confusing. So we're interested in determining this the needed sample size, the sample size n, or the minimum sample size to obtain a needed margin of error within a certain amount. So if we're trying to determine a sample size for mean, determine n sample size for, if we're dealing with mean, we would be using this equation right here. N equals z alpha over 2 times the sample standard deviation divided by E squared. And I'll show you where this comes from. This comes from the margin of error equation. And the margin of error equation, remember, for a that we just mentioned on the previous page is E equals T alpha over 2 times S over the square root of N. Now, what we're doing here, one thing you may notice right off the bat is that in the equation that they give you in the book, it mentions Z alpha over 2. So the reason they're using that is because, if you remember, if you're trying to find a t-score, the only way you can find a t-score is if we have the sample size, because we need degrees of freedom to find a t-score. So we can't have a t-score in the equation to find n, because t is dependent on n and changes as n changes. So we can't have that. So we have to use z alpha over 2. So that's one reason that they have, so I'll just change that to z alpha over 2. And if you solve for n, you would obtain this equation. So I'll leave that up to you to show. It's just simple algebra. And similarly, determine n for dealing with proportions. It depends on the information given in the problem, but we're going to be using the same general equation, and that is I'll just write down the equation before I give the answer. So this is the equation to solve for n for a mean. Now I'm going to start with using E equals z alpha over 2 times the square root of p hat 1 minus p hat over n. Okay, now what we would want to do, I'll just write it right here, we would want to think of it in this form. We want to separate the square root into two separate parts. I'll express it like this. P hat 1 minus p hat over square root of n. Basic property of square roots. Okay. So now we have n kind of separated from our p hats. We have them separated, so we can deal with it a little more easily. And if we were to solve for n, we would obtain the following equation. We would obtain n equals, trying to do this in my head, this might be bad, but n equals p hat 1 minus p hat, and then what we would obtain is, it would go in the numerator, so that would be z alpha over 2 and divide e, and since this is a square root, we would want to square both of those. We'd obtain this. Now, we would use this equation if we were given a given point estimate, p hat. So if they said we think that p hat is this value, it would be given to you in the problem, then we would substitute that value in. If it's not given to you, we would want to maximize our value of n because p hat's not given, so we want to use the maximum value so we obtain a large enough n. We want to be safe if we don't know what p hat is. So to maximize p times 1 minus p, or p hat times 1 minus p hat, that would be using p hat equals 0.5. So we can use calculus, or actually even algebra, using the parabola. We would notice that the max would occur at p hat equals 0.5. So 0.5 times 1 minus 0.5, I'll just write it out. So this is used when p hat is given in the problem. And if p hat is not given, we would use 0.5 minus 1 minus, 0.5 times 1 minus 0.5 times all the same stuff here. And then 0.5 times 1 minus 0.5 is 0.25. And there we go. That is the other equation that's given to you in the book. Now this is when p hat is unknown. There you go. Here's the 3 different equations that you use. As you can see, the 3 things that I squared to determine the sample size n that you remember from Math 243. When p hat is given or unknown. Now let's go over a few examples just to refresh things. Actually, since this is a review, I think you guys can just practice some problems and ask me questions if you need to. We'll make this a quick video with just going over the terminology. You guys probably remember this, but so I think probably the best. I'll just show you the pages that are probably best for reference. This is all the equations that you use from 9.1 and 9.2. This is everything you'll need to use. And of course there's 9.3, which I'll show you in a later video, but going over standard deviation. But here's, if you're given information about confidence interval, point estimate, standard error, margin of error, here's the equations you'll be using. Okay? And if you are asked for the minimum sample size, you want to use these equations here. And one quick note, always round n up. Round n up. So if you have like 136.2, if you have 136.2, if you end up solving, you get 136.2. You do not round down to 136. You round up. Round up. So that's 137. That is what they want. You have to round n to a whole number because you can't take a sample size of 136.2. You can only take a sample size of 136 or 137, but you want to round up because when n goes up, margin of error goes down. And if we want to be within a certain value, and whenever the problem mentions within, they're referring to E. So if they want to be within 0.01, and if you round n down, then E goes up and it's not within 0.01. So if you round up n, then E goes down and you're still within that margin of error that you're looking for. Okay? So anyways, let me know if you have any questions from this. Shoot me, just ask your instructor. It's a quick way to kind of go over things. And if you have any questions and you want to go over it in person, we can always do a Skype video or use the whiteboard online. So anyways, let me know if you have any questions. Good luck.